In this chapter, we'll look at fluid flowing around an arrow spoke and look at the pressure and velocity and then the aerodynamic drag of spokes and compare round, rectangular, and oval or elliptical. A Sapim C X-ray spoke looks pretty much like this in cross-section, and we want to see what its aerodynamics look like when it meets some oncoming wind. As was mentioned a minute ago, there's a very thin boundary layer around the spoke, and air molecules stick to the surface of the spoke at the boundary layer. Let's see what happens to this spoke when various layers of air encounter the spoke. One layer of air hits it dead on in the center, right along where the major axis is, and this point here is called the stagnation point because the wind stagnates or comes to a dead stop at the stagnation point. So all of the energy of the wind goes into slowing the rotation of the spoke. This is the point of maximum dynamic pressure. So let's build this up with a whole bunch of layers of air and see how they compare in terms of the velocity of the fluid as it goes past the spoke. The streamlined flow that we see of layers of air passing around the object is often referred to as laminar flow. The stationary boundary layer is sometimes referred to as the viscous layer. Just to simplify this, we're going to ignore the one extremely thin and slow-moving layer of air that happens to be adjacent to the stationary boundary layer. This is a reasonable assumption because calculations show that there is very little penetration of the viscous layer into laminar flow. Without getting too technical, let's expand what's inside this box, and I'll show you the conclusions drawn by a British mathematician named Milton Thomson, who did a lot of studies on aerodynamics and hydrodynamics. Here is our considerably expanded view. This is the surface of the spoke, and around this surface we're going to consider three layers of airflow. Right here is the stationary boundary layer. This up here is what we call the Bernoulli layer, where the viscosity of the fluid is so small that we call it an inviscid fluid. And this area in here is called a viscous layer, and we're going to further magnify this to look at the viscous layer. If we envision the stationary boundary layer as just a layer of molecules of immovable air, then we see above that four small layers of air that are trying to pass over the stationary boundary layer. This first layer moves very slowly because of attraction between the molecules of the stationary layer and the layer that's trying to move over it. This layer here moves faster, feeling less effect of that, and so on. So that we see that the effect of the stationary boundary layer and the viscous layer penetrates only very shallowly into the Bernoulli layer. The resulting velocity gradient in the viscous layer tails off very quickly, and the thickness of it and penetration into the Bernoulli layer can be ignored. The actual viscosity of the air in the viscous layer hasn't really changed. It hasn't suddenly turned into molasses, but the intermolecular attraction makes it act like it has become more viscous. The penetration of the viscous layer is not always negligible. In this case it is, however, because the spoke is very short and is moving fast, so the time that the viscous layer has to penetrate into the Bernoulli layer is negligibly small. As we saw with the water flowing through a constriction on the pipe, these molecules of air in here are accelerated as they are squeezed around the spoke, between the spoke and the neighboring layers of air, and then we see this type of a velocity gradient where the innermost layer is the fastest, and then as we move away from the spoke, the effect of that acceleration from the piling up of molecules of air decreases to this point here. There's no net energy loss, and the layers of air exit off the back of the spoke with the same velocity as they met the front of the spoke. The velocity of the layers of air moving around the spoke decrease until they reach the point of the ambient velocity of the air that is unaffected by the presence of the spoke. In the next few slides, you'll see some computer-generated flow diagrams that shows air moving in a velocity gradient around a symmetrical airfoil, which really is not that unlike the shape of a SEPEAM Sea X-ray spoke. Here is a wonderful graphic with the reference at the bottom, and we're going to take a minute to look at this graphic in detail. The blue colors represent different levels of pressure, with the darkest blue representing the highest pressure. This area here under the wing, where the blue is very dark, represents a high static pressure and a low dynamic pressure, meaning that the fluid is flowing relatively slowly under the wing. But up here we have a very small static pressure and a larger dynamic pressure, indicating that the fluid is flowing faster over the top of the wing. There is, of course, a stationary boundary layer, but right next to that stationary boundary layer, not moving very far from the surface, is this contour line, which is moving the fastest. And then as we move away, the contour lines showing relative airspeed slow down, and we get to the point where the velocity of the air relative to the wing tapers off and becomes the same as the ambient air some distance from the airfoil. Here it comes with motion. The graphic is called potential flow around a wing, and if you click on a button that says more detail, then you'll see what I'm referring to. Now, I'll warn you, there's a lot of math in this website, a lot of complicated looking differential equations, but take a look at it anyway, and certainly you'll be able to understand the graphic. This computer drawing here approximates the shape of a SEPEAM Sea X-ray spoke, which has a major axis of 2.2 millimeters and a minor axis of 0.90 millimeters. We're going to do a little aerodynamic drag comparison, and we're going to compare that SEPEAM Sea X-ray spoke with an oval perimeter to what we'll call Brand X bladed spoke that has parallel sides. And here we have a length of 2.2 millimeters and a width of 0.9 millimeters. This is the same Brand X bladed spoke with the same dimensions that you were introduced to a few minutes ago. I'd like to add another shape to my table here and try to estimate the drag coefficient, the CD, of an oval or elliptical cylinder. If I go back to these two images that you've seen before and I contemplate this oval spoke, it's clear that it looks a lot less like the picture on the top, with a lot of drag in the wake of the spoke, compared to the more aerodynamic spoke at the bottom. Because the separation of the fluid in the case of the oval spoke appears that it would occur farther to the back, it's reasonable that the drag coefficient of the oval spoke would be less than the drag coefficient of the round spoke, but we have to see if we can find some evidence to substantiate that. This would be a typical ellipse with dimensions A and B. The area is pi AB, and the aspect ratio, abbreviated AR, is B divided by A. In the special case of a circle, let's say this is a round spoke with dimensions 0.75 millimeters. So A and B are equal. The area is 1.77 square millimeters and the aspect ratio is 1. This ellipse has dimensions A and B as shown, the same cross-sectional area as the circle to the left, and it has a aspect ratio of 0.39. And this last one is a Sapim C X-ray spoke. It may not be a perfect ellipse, but it's pretty close to it, and it has an aspect ratio of 0.4. You can check out this reference. What we're seeing here are computer-simulated wake and pressure contours. The wind in each case is coming from the left, and all the way on the left you see a round spoke, and then going across spokes that are increasingly elliptical with smaller aspect ratios. The round spoke with a aspect ratio of 1 has a computed drag coefficient of 1.5, and then moving to the right as the spokes become increasingly elliptical, the drag coefficients go down 1.2, 1, 0.9, and 0.8. Not surprisingly, as we go from left to right, becoming more arrow and the drag coefficient going down at the same time, it's not surprising that we see less drag in the wake of the spoke. You could probably find different test results that show different absolute values here. What's really more important is the relative values, and those clearly show that the drag coefficient of the Sapim C X-ray shaped spoke on the right is about half the drag coefficient of a round spoke shown on the left. The computed ratio is 0.53. If I use that ratio and I multiply it by the drag coefficient shown in this table of 1.17 for the circular cylinder, that would give me a reasonable approximation for the oval cylinder of a drag coefficient of 0.62. Of course, that estimate of 0.62 would not be for every oval cylinder. It's for the one that has the aspect ratio of 0.4, but that's the one that I want because that closely approximates the dimension of the Sapim C X-ray spoke. And when I replace those question marks with the additional data that I have, we get this information here. Now, even if we would disagree about my estimate of the drag coefficient on the frontal area, is still inescapable that the product of that times the frontal area over in the right-hand column is tremendously lower for the Sapim C X-ray spoke. Just to emphasize the point, if I multiply my frontal area by my drag coefficient for a round spoke, I get this CDA. For the Sapim C X-ray spoke, if I multiply my frontal area, which is less, by my drag coefficient, which is less, I get a CDA, which is much less. Back to this earlier slide, when we compare now the spoke with the more or less oval perimeter to the one with the parallel sides, it's obvious that the one on the top is going to be more arrow in its shape. It's also obvious that the cross-sectional area and therefore the mass of the oval spoke is going to be less than the bladed spoke with parallel sides. As we look at this picture of a zip wheel, it's fair to ask, can spokes draft on each other? And it's plausible, but experimentally it's been determined that the spokes are way too far apart, so each spoke is on its own to cut its way through the wind.